Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, welcome back, everyone. We're at our last session, and after the last session, we will make our way to Dave's, where there will be lots of food and beverages, so that will be your reward. Well, actually, maybe your reward is Sean and Wim's talk. So Sean is going to tell us now about a quantum algorithm for computing the unit group. So I'll turn it over to Sean.
Thanks. Yeah, so this is a quantum algorithm for computing the unit group of an arbitrary degree number field. This is joint work with Kirsten Eisentrager, Alexei Kitaev, and Fang Song. So the topic is exponential speedups, trying to find problems where a quantum algorithm is exponentially faster than the best known classical algorithm for the problem. And number theoretic problems have been a good place to look for these, starting with Shor's algorithm for factoring and discrete log. And then number fields provided some more problems. So this started with real quadratic number fields. And when you're given a number field, there are three main hard problems, hard classically, that you might want to solve. One is the unit group. In the special case of the quadratic number fields, that's Pell's equation. It's related to Pell's equation. The class group is another problem you can solve. It tells you how close the ring is to a unique factorization domain. And the last one is the principal ideal problem. This can be used in crypto, and in the real quadratic case, Bookman and Williams had a key exchange system that they designed that they hoped would be harder to break than factoring, in case factoring was polynomial time classically. And so since once we had a quantum algorithm to solve the principal ideal problem, we could break that crypto system also. So after that case, so that's a degree 2 number field, then we went up to constant degree number fields and solved those three problems, and then we've been stuck for a long time. And in the meantime, we worked on some field extensions. We looked at similar problems in function fields. And so the topic of this talk is going to be number fields of arbitrary degree. So there are going to be two parameters for number fields that I'll tell you about, and now it's going to be polynomial time in both parameters instead of just the one. Okay, so there are different applications of number fields. I'll just mention one thing I find interesting that's been happening lately, which is in lattice-based crypto. So lattice-based crypto is one of the main proposals for systems that are quantum resistant. But I do want to point out that whether these are secure against quantum computers is actually an open question. It's not been, it's not been decided yet. And a special case, just recently, a special case appears to be broken. So this is used in a few different crypto systems. So it's not like the majority of the lattice-based crypto systems, but there are some cases. The first one is Soliloquy, which is a crypto system that GCHQ was developing. The second one is multilinear maps, and the third one is a homomorphic system by Smartin for Calderon. And
are these broken?
They all use the same assumption, so they're all broken, yeah. And so I can't tell you how it works in this talk, but Chris Pikett has a really nice write-up on his webpage. So if you look on his webpage and you see I explain here, it's a link and you can click it. And if you follow that link, it's really nice. But I'll tell you that the ingredients for breaking this are the work I'm going to talk about today. And then Biasi and Song added the principal ideal problem on top of this. And the approach to breaking this uses something that Dan Bernstein had talked about a year ago. One thing that was missing was solving bounded distance decoding in the unit lattice. And in this GCHQ paper, they mentioned that BDD in the unit lattice can be solved classically, efficiently. And so the people from the crypto community went and proved that it's actually possible. So when you put that all together, then the assumptions from these systems can be broken. Okay, but I want to talk about the setup for computing the unit group of a number field. And as with a lot of exponential speedups, it goes through the hidden subgroup problem. So I want to tell you what that is or remind you what that is. Okay, so this is just an abstract problem that you can define and you can try and solve it. And so the problem is you're given a function f from a group to a set, and it's constant and distinct on cosets of some unknown subgroup H. Okay, so you can imagine, here you have all your group elements. You have a function that you evaluate. There's this unknown subgroup H, and when you evaluate it on H, you get the same value. A different coset, you get a different value. And in this case, there are different colors if you can see them. And you should think of G as exponentially large. So you can't just query the function everywhere. You want to run in something like time log group size, polynomial log the group size. Now, depending what the group is, we sort of, it determines how hard the problem is to solve by a quantum algorithm. So some examples, when G is abelian, we have quantum algorithms for all or most cases. And this is the way these quantum algorithms work. So for example, factoring an integer n reduces to solving a hidden subgroup problem over the integers when the group is the integers. Discrete log reduces to the case where you have this finite group, zp minus 1 cross zp minus 1. Pell's equation moved to the reals. And now for this general degree unit group, we're going to solve it for r to the n. So that's where we're going to go. And now, I'll just mention there are still these important open questions for the hidden subgroup problem about non-abelian groups. If you could solve this for the symmetric group, then you could solve graph isomorphism. And if you could solve the hidden subgroup problem for the dihedral group using the usual method that we try and do, then you could solve the unique shortest vector problem. So those questions are still open. Okay, so here's an overview of the way the algorithm is going to work and the talk is going to work. So the input is going to be a number field. I'll tell you about what that is. And there's a reduction to a hidden subgroup problem in the middle, and then we give a quantum algorithm to solve that hidden subgroup problem. So this is the order I'll go through. The main thing I'll do in the talk is I'll talk about how you set up a hidden subgroup problem from the number field. I won't have a lot of time to say much about the solution to the hidden subgroup problem over r to the n. But let me just mention that, in terms of trying to generalize the previous algorithms that solved the constant degree case, there were two main roadblocks for going to arbitrary degree. So the first roadblock was in item 3, trying to reduce the problem of computing units to a hidden subgroup problem. Previously that reduction, if you tried to use the same approach, would take exponential time. And one of the ways one of the things that we have in our solution now to fix that problem is we have a new definition of a hidden subgroup problem that's over continuous groups. And once we have that, then we actually end up with a quantum reduction instead of a classical reduction, and we're able to get that to work. And then the second roadblock was solving the hidden subgroup problem over r to the n. The problem is once the dimension grows, so you're over the reals, and so you're rounding stuff off everywhere, and then you're getting to high dimensions, and you try and do Fourier analysis on that, and the errors are just really hard to understand. So now that we have this continuous version of the HSP, we were able to set it up and analyze it. Okay, so I'll start with the first one, which is describing what the input looks like to the problem. Okay, so I'll give you two examples of number fields to try and give you an idea what the parameters look like and what the fields look like. So here's the first example. We have Q adjoint square root D. So this is the set of numbers A plus B square root D, where A and B are rational numbers. D is a positive non-square integer. Okay, so this is a field. So you have addition, subtraction, multiplication, division of all these numbers. And the input to this problem, so I can describe to you that I want to work in Q adjoint square root D by giving you D. So you can think of D as being the input. When you generalize it to other fields, you talk about the discriminant. And so here the discriminant is something like D. So that's the input size. And then the degree is 2 for this number field. So these are the two parameters, the discriminant and the degree. The degree is 2 because if you look at it, it's a degree 2 vector space over Q. A and B are the two parameters, 2 degrees of freedom. So the goal, when I give you this number field to be polynomial time, you want to be polynomial time in log D. The degree doesn't play a role because it's a constant. Okay. Now here in this talk we're interested in higher degree number fields. So here's an example of one. It's the cyclotomics. So you take Q and you join n through to unity. So here omega n is e to the 2 pi I over n. And so for example, if n is prime, then we can say something that the discriminant's about n to the n, and the degree in this case is n minus 1. If you see, you have a0, a1 up to an minus 1. Oh, is that right? Okay, maybe that's not right. That looks like degree n. I think that should be n minus 2. Yeah, it should be an minus 2. That's a typo. But anyway, so to be polynomial time in these two parameters, be polynomial in log the discriminant and the degree, you want to be polynomial in n. So that's the goal. Okay, so here's some running times for unit group algorithms. Now, factoring is not an example of this, but just to compare the running time, the best factoring algorithm is something like e to the n to the 1/3. You can also reduce it to computing the unit group in Q adjoint square root d if you want to have a slower algorithm. But the best classical algorithm for Q adjoint square root d is something like e to the n to the 1/2. For general number fields, it's exponential in n and m, or with heuristics, maybe it's sub-exponential, but it still is exponential. The previous quantum algorithm was polynomial time in log the discriminant, which I've written as n there, but exponential time in the degree, m. And so here we're going to have polynomial time in n and m. And please ask questions as we go, if anybody wants to ask anything. Yeah?
One question. So
Yeah. Oh.
I know maybe it's a little bit too early. What's the output of your algorithm? Are you going to talk about like what's the precise output?
Yeah, I'll talk about the output. Next slide. Okay. So here, so I'll give you, okay, so that was the input, number field. Now we want to talk about the output, which is the unit group. So let's talk a little bit about the unit group at least. Okay, so in general, you're given a field, Q adjoint square root d. Inside that is a special ring called the ring of integers. And so if you look at the multiplicative group there and you ask for the invertible elements, that's called O star. And that's the unit group, O star. It's the invertible elements of this ring. So I'll just give you two examples. So a not so exciting example is if you just take Q, and then the ring of integers in that case are just the integers. And the invertible integers under multiplication are just 1 and minus 1. Okay, so that's not so exciting. So we can move on to, say, Q adjoint square root d. So here we're looking at these numbers a plus b square root d. Now, I don't know if this is a pointer or not. Maybe not. Yeah, there we go. Now, the ring of integers doesn't always have this form, but sometimes it has this form. So I'm just going to write it like this because it's nice to look at. So you can think of a lot of the cases as the ring of integers as being numbers of the form a plus b square root d, where a and b are now restricted to be integers. Okay? And now we're looking at what's the multiplicative subgroup of that that is invertible. Okay, the multiplicative subgroup. And so at least the infinite part, I've left out some finite thing here, but you can think about the infinite part as being generated in this case by one element, by Dirichlet's unit theorem. This is called a fundamental unit, and to get the whole unit group, you would just take powers of this element, positive and negative powers. And so the goal would be to find u. If you had the fundamental unit, then you would know the unit group. Okay? So here, I'll give you an example of a unit. Okay, so here's a number field. Let's take d as 109. So we're looking at q adjoint square root 109. And here's an element from the ring of integers. So we have an integer coefficient here, an integer coefficient here. And for this thing to be invertible, we need something with the same form. We have integers, and when you multiply them, you get 1. And so here's the inverse. It's the same thing, actually, with the sign flipped. So it's easy to see here. And if you multiply them, you get the first number squared minus the second number squared times 109, and that's 1. Okay? So it's a concrete example. Now, you may notice something here if you're used to thinking about running times, which is the input has 3 digits and the output has whatever, lots of digits. And one of the reasons I'm showing you this example is because that's actually a problem. So in general, If you just wrote down the units in this representation, they can have doubly exponential size. So it would be impossible to have a polynomial time algorithm because you can't even write down the output. So we make one more change, and what we do is we just take the log of O star. So we take the log embedding in general. So O star was a multiplicative group, U to the K. If we take log of everything, it's going to change it to an additive group. And now you're looking at a lattice in general when you move to higher dimensions. So this is a one-dimensional lattice. You're trying to find log U. And in general, you're going to be finding a basis of a lattice. And we don't even need log U to a good precision. We just need it to some precision. We can round off. Everything's fine. So does that answer your question in terms of what? Does it get closer to answering your question?
I guess, yeah, but I just don't get details how it's actually, why it's efficient to have just, just to know log to some precision. But yeah, maybe I'll just take it offline.
Yeah, I can't answer that easily, but there are algorithms that deal with approximations and let you test for units and things like that, especially in the real quadratic case. It's harder in higher dimension, but. Okay. So that's the input and the output. Are there any other questions before I move on to the hidden subgroup problem? Yeah?
Is it the case that you know the group of units but might not know the exact expression for any unit in that group?
The exact expression.
Like here you said.
Yes.
Approximation gives you the group structure, but not necessarily the knowledge of the actual unit.
In this representation, yeah, you have approximations of the units. Yeah. There are other representations you can try and compute that are exact, that are like factored in certain ways. But this representation is rounded off.
Can I ask a question?
Yeah.
So you're saying the output is the basis for the group of units, right?
Yes.
And
The output is the basis of the group of units.
Yeah.
Yes.
the actual question that I want to ask is different one.
Okay.
I wanted to go back to your earlier slide. So are you going to tell us how this is related, like through the HSP back to the hard problem for the crypto systems, or are you not covering that anymore?
No, yeah, I can't cover. I'll just mention, on the last slide, I'll just mention what their assumption was.
Okay.
But, yeah.
Thanks.
Anything else? Okay. Okay, so we want to reduce this problem to a hidden subgroup problem, and it's going to be over R to the n. So we have to talk about this issue. Like, how do you even define hidden subgroup problem over R to the n? What happens when you try and do it? Okay, so if you're familiar with the integer case, say periodic functions, we can think about periodic functions as a special case of what we're doing here in one dimension. Then the function, a hidden subgroup problem, a function that satisfies the hidden subgroup property would be periodic. So this would be the subgroup. It would be, let's say, multiples of R here, 1R, 2R, 3R. If you evaluate the function, you get these different colors. And it would be 1-to-1 on the period. So it would take different values in here. Okay, that's the basic property for the hidden subgroup problem over Z. Now, once you go to R, you could say the same thing. But the problem is the period could be irrational or transcendental. You may not even be able to write the period down, right? So if you can't write the period down, how could you compute with it? Like, you can't even, nobody can give it to you, and if you had it, you couldn't verify it. So we have to do something with the function in order to make the information accessible to us. And what we did in the constant degree case, what we did is basically the very first thing we did was round everything off, and we dealt with rounded things right from the beginning. And that gets into trouble when you try and go to high degree. And so here what we're going to do is define a new hidden subgroup problem. It's a continuous one. So now it's going to go from R to the n to quantum states, not just to any set. Usually it might go to basis states, standard basis states. But now it goes to quantum states, so x gets mapped to some quantum state f of x. And it's going to have three properties now. So the first one will be periodic. This is just rewriting periodic with inner product. Now, as far as being distinct on cosets, we can't make it distinct on cosets. Otherwise, you're going to have this problem of you have to evaluate it directly at the point. So what we'll say instead is we'll let the inner product drop off exponentially as you get farther from the lattice. In one dimension, it's a one-dimensional lattice. So here I've graphed the inner product, for example, of f of 0 versus f of t. And so the inner product between those two states is going to fall off. And then you'll be back to inner product 1 at the period. Okay, so this is how we handle that. Now, we still might have a problem if it falls off too fast. We still wouldn't be able to query near R. So the last condition will be Lipschitz. So Lipschitz limits how fast the function can change. Right? So f of x minus f of y is at most x minus y times a. Now, what this does for us is it makes f of r almost the same state as f of r plus epsilon. So we can just set down a grid on here relative to what the Lipschitz constant is, and we're free to evaluate it at these other points. So these 2 points would be close to f of r, almost the same state. And we can do it. We can get access to the information that way. Okay. So that's the continuous HSP definition. So one thing we're going to need now is some continuous functions. So I'll show you a place where we can get a continuous function. Okay, so we're going to be dealing with lattices and real valued lattices, and we're going to have to round points off. And this creates a problem in quantum computing because you can't just write down approximate numbers that are close because these two states are just complete, they're orthogonal. But what we'd like is that to have them be close. And so we have a way to encode real numbers that's going to take care of this called the straddle encoding. And this is an example of a continuous function. So a real number x can be mapped to the straddle of x, which is, it's basically sitting on x and x plus 1. So I'll show you an example down here. So it's the cosine part of the fraction here and the sine part here. So I have a little thing here. So here's basis state 1, 2, 3, 4. And if I let this go, it'll show you the straddle encoding of different values. Okay, so that's the straddle encoding. It's a continuous function. And it has some nice properties. So one property is that if two values are close, suppose we're looking at x and x plus epsilon, these are real numbers, their straddle encodings will have very high inner product. Because if x is black here, that's the higher one, and the lower one here. And if you move over a little bit, it just changes this a little bit, so they still have high inner product. On the other hand, if you take another value y that's farther away, then the inner product is just 0. So that's something we need in our analysis later on. We initially were trying to use narrow Gaussians for things, and we didn't have this inner product 0, and it made it hard to do stuff. So this solves that problem. Okay, and as a lemma, we can show that the hidden subgroup problem over the integers, or basically, all the known cases reduced to the hidden subgroup problem over the reals, or high number of copies of the reals, and we can use the straddle encoding to do that. So we can take the integer valued one and make it continuous, and then so our algorithm subsumes the previous ones. Okay, so that's the continuous hidden subgroup problem. So now I'm going to tell you where we get this hidden subgroup instance from the number field. Okay, how do we take this and define one of these functions that we can compute efficiently? It satisfies the properties. Okay, so I've been saying lattice in case people, in case you're not familiar with lattices, let me tell you what the definition is now. So a lattice in n dimensions, you're given n vectors b1 through bn in R to the n. They're linearly independent. And the lattice is the set of all integer linear combinations of the basis vectors. So here's an example in 2 dimensions. So b1 and b2 are, say, a basis, and you take all integer linear combinations, and you get this infinite grid. And there are an infinite number of bases for a lattice. So there are an infinite number of bases for this lattice. So for example, here's a different basis for that lattice. And if you hear people talking about hard lattice problems, if you're not familiar with it, one hard problem is given a basis for a lattice, find the shortest vector. Okay. So when you look at this picture, you may say, oh, I can see the shortest vector. It's right there, and it's right near that one basis vector. But in general, the basis you're given can be very skewed, very long, and it's unknown how to compute a short vector. And there are a few other problems, too, that are hard, but that's one of the main ones you may hear of. Now, the basis, I mentioned before that we're computing the log embedding of the unit group and that it's a lattice. So this is the type of object we're looking for. We're trying to find a basis for the unit group, a basis for the lattice. Okay, so I'll try and give you the idea of where the hidden subgroup problem comes from. I'm going to use Q adjoint square root D, so this is constant dimension, but I'm going to show you that because I can actually draw pictures with that. But I want to just remind you that the reason we're doing this, setting it up this way, is so we can handle high dimensions. Okay? So the basic idea is you take your function and you take your real number here, t, in this case it's going to be just r, and you map it to principal ideals. So a principal ideal is an ideal in O that's of the form alpha times O. Okay? And the way the definition works is I'll say that t gets mapped to e to the t times O. So e to the t is supposed to represent the generator for the ideal. But the actual definition looks like this. So if you're given a vector x, y, this is what e to the t is. It's e to the t, e to the minus t, and it does an exponential stretch in the x direction and an exponential shrink in the y direction. Okay, and if you think about this, it's periodic on the units. You know, epsilon O equals O if and only if epsilon is a unit, and that's also true for any ideal. So that gives you periodicity, and it's also 1-to-1 on the period for the same reason. So it's going to satisfy those two of the basic properties we need. But the main issue is going to be how to represent e to the t times O. You know, we need to now come up with a quantum state that represents this real-valued lattice, and you know, how do we compute it? It's really important that we have a unique representation to get periodicity, and so that's the type of thing we're dealing with. So I'll try and make this. I'll show you a picture of what this looks like. What type of ideal you get out over here. So in this case, it's going to be, we'll think of it as a two-dimensional lattice. So you can always take these ideals and embed them. So here's an example with Q adjoint square root 102. Okay? And the ring of integers in that case has generator square root 1 over 2. And when you do this embedding, I'm not going to define what the embeddings are, but this is the way the embedding works. In this case, it's generated by 1, 1 and square root 1 over 2 minus square root 102. So these two green dots are the generators for the ring of integers. You take all integer linear combinations. That gives you the ring of integers. So this is the lattice you start with. And then you want to multiply this times e to the t. That's the output of the function, e to the t times this lattice. Okay? Now these lines I've drawn here are the algebraic norm lines. So the algebraic norm is defined as the x-coordinate times the y-coordinate in this lattice. And when you do that stretch map, you know, if you multiply x times e to the t and y times e to the minus t, you're going to stay on the same norm line. So when you start multiplying by e to the t, a point is going to move along this algebraic norm line. So they're all going to move like that. That's how the lattice gets deformed or stretched. Okay, so here's an example. I'll show you a little animation here of what happens when you evaluate this hidden subgroup function on different values. Okay, so here's the domain. It's R. So this is going to move across here. And over here, we're going to output e to the t times O, which is going to be the stretched lattice. Okay, well, it stopped. Well, if you keep going and you go back to here, then you'll end up with the first picture that I showed you. Oh. Okay. Questions? Okay, so that's the function. So the idea, so I guess I'm still telling you what the idea is. So the idea is you want to take f, map it to some sort of unique representation of e to the t times O. So now for each of those lattices on the previous page, we need a unique way to represent them. And if it was an integer lattice, that would be okay, because the Hermite normal form is a unique representation of a lattice that's over the integers. But over the reals, there's no unique way to represent a lattice. You know, it's this infinite object, so you have to specify it by a basis, but there's no canonical basis you can pick for a real-valued lattice. So that's one of the things we have to deal with. So there are two new self-contained parts here. The first is a polynomial time classical algorithm for computing a basis for e to the t times o. One of the issue here is that e to the t is doubly exponentially large, because t is going to be exponentially large. And so we're dealing with rounding errors, and you know, it's something we have to deal with, yeah. And the other way is how to represent the lattices. So what we do is we first compute a basis, classically, and then we create a superposition over the lattice points of that lattice. So this is what it looks like. We use the straddle encoding. So you can think of, so G is like a Gaussian, so we have like a Gaussian weighted lattice, where around each point we have the straddle encoding. So this picture has narrow Gaussians. That's originally what we were using, but now it should be like, you know, these spikes that go up for the straddle encoding. So the straddle encoding handles the rounding of the lattice points, and as a result, this state acts basis independent. It can't actually be basis independent, or it wouldn't be a reversible operation to create it, but it, you know, acts basis independent. That's what we have to prove.
The spikes are supported on an exponential number of points, right?
Yes.
Because it's high-dimensional, 2 per each direction, is that correct?
Oh, you mean straddle? Just straddle of one point?
Right.
Yeah, yeah, it's on an exponential number of points in high dimension. Yeah. Yeah, two in each one. Okay, yeah, so then we have to prove that this is a hidden subgroup function, and we can compute it. I'll just say one thing about computing. So the first step is computing a basis of e to the t times o. And you know, so basically you want to use repeated squaring, because if we're dealing just with principal ideals here, so we can take e to the t times o, multiply times e to the s times o, we get e to the t plus s times o. So that's good. But we have to make sure the representations aren't getting too big and the rounding is working, because this e to the t is going to be doubly exponentially large. So what we do is we alternate two steps. So the first one is we think of these as ideals, and we multiply them like we do here. We have them written down as vectors, even though they're ideals. But given two vectors, the way you multiply it, once you embed them in these embeddings I mentioned, is just pointwise multiplication. So we can do that, keeping track of the errors. And so given 2, you just compute all these products. So that's the first step. And then the second step is we need to reduce the representation size so it doesn't grow too big. And for that, we then we think about these ideals as lattices, and we compute an LLL reduced basis for them. And then we just alternate these steps. So an LLL reduced basis is going to keep the basis polynomial size, and the determinant doesn't change as you do these stretches if you pick everything right. So that's going to maintain the size of the lattice because the determinant's not growing. And the other slightly tricky thing is when you're doing LLL on rounded basis vectors, you can't just run it because it'll, the rounding messes up. It doesn't know when to stop reducing. But since if you have a lower bound on the shortest vector length in your lattice, then there is a way to do it. And since we're in ideal lattices, we do have a lower bound on the shortest vector length. So we can make that work. Yep. Vadim? Oh.
One question. So is it like LLL here runs on a quantum computer or on a classical computer?
This would be on a quantum computer.
On a quantum computer. Okay.
You mean are you asking if we're doing it in superposition or something like that?
Yeah, I mean
it's not a pre-processing.
Yeah. So
is it a pre-processing step? Okay, sorry.
I mean, I'm just kind of curious. Do you need to implement, LLL inside your quantum computer, or it's just pre-processing? Right? So.
Let me think for a second. Yeah. It's in the quantum computer because at least intuitively, you would want to be in a superposition of t values and then evaluate f of t.
Okay.
So you're evaluating that in superposition. So
Okay.
all this is happening in
Okay,
superposition.
cool.
Yeah.
Yeah. Yes. Thanks.
I don't have any gate counts.
That would be my question.
So I'm a little confused at what things are simplified because we're describing it in lower dimensions versus what's required for the general degree case. So is T always a number, or is T some kind of a more general transformation? Because you do this hyperboloid before, and T
Yeah.
was kind of telling you where you were on that, but now you have some higher dimensional thing, right? So is
Yeah.
T a matrix or something, or?
Yeah, oh, this is the general thing. Well, it's, you have a diagonal matrix e to the T1 through e to the
Oh, I see.
Tn,
Oh, okay.
and their sum is 0. So I'm going to make sure you preserve the determinant of the lattice as you go through.
Sure, I see. Thanks.
Yeah. Okay, and so then we have to prove the HSP property. So here I'll just give you an idea of what we have to do. So for example, we want to know how much overlap there is, because we would need to prove that there's overlap when you're off by a unit and small overlap when you're not. And so you would compare like O and e to the t times O. So these are these two superpositions of lattice points for different values of t. So if t is not close to a unit, you want to have small overlap. Okay, this picture isn't accurate because there's no one-dimensional case, but if I draw it in one dimension, then it's easy to look at, right? So you can imagine here's a superposition over lattice points and another superposition over lattice points, and since the values aren't close, it's a small inner product. And when it's close to a unit, you want high overlap, and that's going to be something like this. You can just imagine shifting your lattice a tiny bit, and the straddle encodings are still overlapping a lot, so you have high inner product. And then we have to prove some number theoretic properties about when these transitions occur to make sure that that lattice points aren't too close in ideal lattices and so on as we stretch them, and we prove the HSP property. Okay, so that's that part. That's how you set it up. So maybe I'll just say a few things about the high degree HSP case. So that's the last step. So here's the problem we want to solve now again, just to remind you. So this continuous HSP, it's on R to the n, takes values of quantum states, and has these three properties. So it's periodic, distinct on cosets, and in Lipschitz. We're trying to figure out what this hidden lattice is. Now, the intuition is sort of something we've understood for for a long time. If you want to solve this type of thing, you evaluate your function in superposition. You measure your function value. You end up on a random coset of the lattice you're trying to find, V plus L. So because you have this random thing in here messing it up, so you can't just measure this, you compute the Fourier transform. Then you're sitting on the dual lattice. And now if you measure, you get a random point of the dual lattice. So you would repeat this polynomial many times where you get a point of the dual lattice. Once you have a set of generators, you can compute the lattice from the dual lattice. And that's the way the algorithm should work. Right? So the problem now, though, is there's more going on because we're in a real valued, we have real valued points. So these guys are all getting rounded all over the place. And Fourier transform over which group? Lattices are infinite objects, and you have to cut things off somewhere, and it's in high dimensions. And so if you start just trying to grind through it, like with the constant degree case, you can see that maybe you find some points somewhere, and some points might be missing, and places you just can't even analyze it. And so the reason the constant degree case worked is because we could analyze it in a point around the origin, that in some region around the origin you would get good points, and because it was constant degree you had a high probability of measuring those points. But now in high degree you have an exponentially small probability of measuring in that location. So that's the problem. Okay, yeah. So what we did differently this time, since now that we have this continuous function, is basically we just kept everything continuous for as long as possible and only rounded off at the very end of everything. So first we analyzed everything in the continuous world. We could use generalized functions, and we could think about the superpositions like this. You know, like this is evaluating the function in superposition, and we compute the Fourier transform over r to the n. And now there's these round-off errors aren't hurting us yet. And so we end up getting some commutative diagram where this is what I drew on the previous slide. If you had started here and you get over to here, you want to try and analyze that. There you want to try and show that you're concentrated, that this thing is concentrated on L star. And then you want to discretize stuff. So you actually only want to evaluate your function on a grid. So you can think of restricting this down to z to the n, instead of r to the n down to z to the n. So now you're on a grid, and compute the function over Fourier transform over z to the n. And then if you discretize, if you get discrete samples out of this thing in the end, then that's finally what the algorithm is. So that's what we do. We analyze these things like this, you know, this and the whole diagram. We show the diagram works and what happens when you discretize. Okay, so I think that's all I'll say about that for now. Okay, so recap. So showed you how to set up an algorithm to compute the units of an arbitrary degree number field. Biasi and Song have extended this to the class group in the principal ideal problem. So the assumption in the crypto system that I mentioned in the beginning, I'll just mention what it is. It's something called, you know, short generator principal ideal problem. It was used in these three crypto systems. So if you think about the sequence of assumptions you can make in lattices, you might start with lattices, say, over the integers. And then you could make the assumption that you take a special case of ideals from number fields, which is what they do to make things more efficient. And then you could say, well, instead of using ideals, we'll use principal ideals. And then you could make another assumption and say, not just principal ideals, but principal ideals with short generators. Okay, so that's the assumption that was made in here. So these types of lattices, and that was the one that was broken. So in their case, it's for power of 2 cyclotomics. You can use quantum algorithms to get some generator for the principal ideal, and then the classical algorithm that I mentioned, you can compute a short one by solving BDD in the unit lattice. Okay, so open questions. There's still more number theoretic problems, towers of number fields, Hilbert class fields. I think that this result with the lattices is pretty exciting. I mean, I don't know what will happen next, but I think it's still good to know if the shortest vector problems are hard in these bigger classes. And there are other homomorphic schemes, circular security, and lots of questions there. So I'll stop there. Thanks.
Anyone have any questions? Kristen?
So you mentioned on one of your first slides that quite a bit earlier you had worked on the unit problem for constant degree. Mm-hmm. And so it wasn't totally clear to me, like, obviously you talked in this context about that how it grows as the degree, goes to infinity. But are you saying that for any fixed degree, which is true for crypto, like you just take some instance of soliloquy and it's for, let's say, degree, n equals 256 or whatever it is, that you actually had algorithms that would have worked before that for that constant degree? And if so, like, how do they compare? Because usually you hide all the constants, terms, and things like this. How do these algorithms compare to what you had before?
They're quantum algorithms.
Well, on one of your first slides, didn't you say that in 2005 you already had algorithms for finding
a quantum algorithm? Yeah.
Quantum algorithms,
quantum algorithm, yeah.
So how do they compare? Like, the degree is actually fixed for crypto. That's something that people usually ignore.
Right. Well,
so for a fixed degree, how do they compare?
These are asymptotic results, though. I mean, I'm not even thinking about. I don't even know how you would compare it. Are you talking about like running it?
Yeah.
Okay. Do you need a quantum computer for that, though? Or?
Well, you estimate it, right? Like, how do they?
Oh, I don't know.
You don't know.
Yeah. Oh, I guess. Yeah, maybe. Somebody could do that, I think. Yeah.
Yeah, that's the question I was going to ask is what kind of cost do you think, if you This is asymptotic with constants, with numbers of qubits, numbers of gates.
Yeah, this is
How hard do you think this would be on a quantum computer?
hard.
Any other questions? Okay, well, on that note, we'll invite Wim to come up. Let's thank Sean again.